Hello everybody, my name is Jason. I'm a second year engineering science student at the University of Toronto, and today I'll be talking about the course ESC194 Calculus 1. Today is December 20th, 2021. Normally I would be studying for an exam right now, but my last three exams got cancelled by the university because of COVID, and so here I am making this video. So first off, what is ESC194? It's a course I took last year during fall. It's a compulsory year one fall course in the Engsci program at U of T. When I took the course in fall of 2020, the two professors were Professor Stangeby and Professor Davis. Throughout the course, we begin by talking about limits and continuity, specifically delta-epsilon proofs. Uh, we talk about derivatives, and we talk about important calculus 1 concepts like chain rule, implicit differentiation, other rules for differentiation, etc. Mean value theorem is also pretty important, and we also talk about optimization problems with derivatives. There's also curve sketching. There's a lot of this course revolves around curves. We talk about antiderivatives as well as integrals, specifically a fundamental theorem of calculus, U substitution, also known as substitution rule, and we also get into applications of integrals such as finding the area between curves, volumes of revolution, the average value of a function, and interestingly enough, we also talk about differential equations in this course, even though it's not in the course title. So we talk about solving linear first order differential equations. Uh, I believe we do this using the integrating factors method. Uh, and we also go through linear second order differential equations. We went through variation of parameters um, and undetermined coefficients, which is interesting because it actually comes back in second year. Uh, so yeah, kind of funny. But today I'll be going over a midterm question that I did during the fall. There were two midterm tests. This is from midterm test 1, which was administered quite early actually, October 15th, 2020. And the topic of this quiz is the delta-epsilon definition of a limit, which is probably one of the most notorious topics in this course, probably one of the most feared as well by students. And this is the question. So it's very straightforward. Prove using epsilon delta arguments that this limit is true. So we have a wild function, square root of absolute value of x minus 1 divided by 2 plus x squared. And it's basically asking us to prove that the limit of this function as x approaches 1 is equal to 0, which should be pretty intuitive given that as x approaches 1, the numerator just goes to 0, the denominator goes to some constant value that's non-zero, and so intuitively it should be 0, and we're going to prove that it is. So just to refresh ourselves on the delta epsilon style of proof for a limit, if we want to prove that the limit as x approaches c of f of x is equal to L, we need to show that for every epsilon greater than 0 that is imposed, there exists a delta greater than 0 such that for every x, this inequality holds, which basically says that um, we can define a neighborhood around the value c, which defines a set of x's, which implies that in this neighborhood, the absolute value of our function evaluated at any x in this neighborhood minus L should be less than the epsilon imposed. In sort of in a more eloquent way, we can say that if we're imposing a certain range for which our y values should be within, we need to ourselves find a relationship between the y values that we're restricted to the x values that we're restricted to, such that our function actually doesn't go out of the bounds that are imposed on the y values. So in order to do this, first we need to find delta in terms of epsilon. And we do this because then, obviously, for every epsilon imposed, we can just say that delta should be equal to so-and-so so that this is satisfied, this condition. And then second of all, we need to construct the proof, obviously. So for this problem, given epsilon, we need to find delta. So to reword the problem, or plugging in our values of f of x and c, basically we want to show that for delta around the value, for x values around 1, we want to show that the absolute value of our function is less than epsilon. And that's just because we're trying to show that the limit is equal to 0. So we want the absolute value of our function to be less than epsilon. So we should notice, first of all, that this quantity, the absolute value of x minus 1, appears in f of x, which means that we can show that the square root of this absolute value of x minus 1 is less than the square root of delta, and that's because the square root function is monotonically increasing. And now we want to deal with this denominator. Again, we have our numerator in a relationship to delta. How do we deal with this denominator of 2 plus x squared? Because it doesn't seem like we can really massage much out of this x minus 1, right? In order to do that, we can put a bound on delta. So let's just say delta is less than 1. This is totally arbitrary, but it's just what I did because the number 1 is, nice and small. So we can say because delta is less than 1, the absolute value of x minus 1 should also be less than 1, which implies that x minus 1 is between minus 1 and 1. Just adding 3 to this entire line, we find that x plus 2 is between 2 and 4. Squaring everything, we find that x plus 2 all squared is between 4 and 16. And the reciprocal would be between 1 over 16 and 1 over 4, which shows that this whole expression, 1 over 2 plus x squared, is less than 1 over 4. Now, this is very handy because this is exactly the form we wanted in, because if you recall, in our function, we have a factor of 1 over 2 plus x squared. So now we know that our numerator should be less than square root delta, and we know that our denominator should be greater than 4. So therefore, when we're constructing this inequality, we can say that our f of x minus L, all absolute value, is less than the square root of delta divided by 4. And recall that we want this expression on the left-hand side to be less than epsilon. So therefore, we can choose delta such that square root delta over 4 is equal to epsilon, which means that delta is equal to 16 epsilon squared. But also remember that we set an upper bound on delta. So therefore, our actual definition of delta should be the minimum value of 1 and 16 epsilon squared. So if epsilon becomes large, we can just say that delta is equal to 1. Now we need to construct our proof. So to do that, we need to show that for every x, this inequality implies that f of x minus L absolute value is less than epsilon, given that we know our definition of delta. Since delta is less than or equal to 1 by definition, since it's the minimum value of these two, and it can never be greater than 1, then we know for a fact that because the absolute value of x minus 1 is less than delta, we know that our function is less than square root delta over 4. And because we know that delta is less than 16 epsilon squared, we know that f of x is less than square root of 16 epsilon squared divided by 4. And by simplifying this, we can show that this expression, f of x minus L absolute value, is less than epsilon. And so we've proven that the limit as x approaches 1 of f of x is equal to 0. So we can visualize how changing epsilon changes delta and how this shows that the limit is equal to 0. So in this picture, the red curve is equal to f of x. And you can see there's a cusp at x is equal to 1 due to that absolute value sign in the square root of the numerator. And the horizontal lines represent our boundaries given by epsilon, and the vertical lines represent our boundaries given by delta. So when epsilon is equal to 1, 16 epsilon squared is 16. So therefore, our delta will be equal to 1 because delta can never be greater than 1. And as you can see, within this box, our function never crosses the green or purple line, which is as we expected. So if we have epsilon to 0.5, we notice that delta doesn't change. It doesn't have to because 16 epsilon squared is still greater than 1. And as you can see, this satisfies our hypothesis because our function is still within the box. It doesn't cross the green or purple line in this interval of x's. So as we shrink epsilon further, we find that at this point, 16 epsilon squared is actually equal to 1. So delta is still 1. And at this point, we see that our curve intersects with this corner of the box. So it's still totally contained within this box when the x values are between 0 and 2, non-inclusive. And now we should see a drastic change because as we have epsilon once again, our value of delta should change because now the term that's deciding delta is the 16 epsilon squared. So now delta is 0.25. And we needed to shrink delta because when we're shrinking our bounds for epsilon, we need to shrink delta so that the function remains within this box and that it doesn't cross the green or purple line in this interval. So we can have epsilon again, and once again, delta shrinks. It shrinks by a factor of 4 because delta depends on epsilon squared. And we can see that even still, in this box, the function does not cross the green or the purple line. And we can keep doing this, but we've shown mathematically that as we shrink epsilon, delta should shrink accordingly so that this function should never cross the upper or lower bounds that are defined by epsilon, and therefore the limit of this function as x approaches 1 is equal to 0. So I'd just like to make some quick acknowledgements before I end the video. So thank you to Professors Stangeby and Davis for the course and the midterm test content. Also like to thank the tutorial TAs for the tutorial section that I was in, Amzil, Jeffrey, and Alex. Also like to thank the individuals whose Beamer template I took from, Kastner and De Silva. So thanks so much for watching, and then take care.